Welcome to Calculus. Today we will investigate graphing tangent lines of relations by implicit differentiation. Let's take a look at one example. Our function here is a circle. We're looking at x squared plus y squared equals 5. And in fact, it's not a function, it's a relation. So we want to find the slope of the tangent line to this circle at the point 1, 2. Once we find the slope, we want to write the equation for the tangent line, and then to finalize, we want to graph both the tangent line and the circle on this coordinate plane. Well, let's start off with that first task of finding the slope of the tangent line. So I've got to remember that the slope of the tangent line is given by the derivative of the relation. Now, since it is not a function, I do need to use implicit differentiation, but let's go ahead and do that for this circle. So I'm going to take the function x squared plus y squared equals 5, and let me take the derivative of both sides. So that's d dx of x squared plus y squared equals the derivative of 5. So as we do with implicit differentiation, we start by taking the derivative of both sides. On the left side, I need to employ the sum rule. So that's the derivative of x squared plus the derivative of y squared. And on the far right side, I can go ahead and take the derivative of the constant 5. That's going to be 0. Returning back to the left side, the derivative with respect to x of x squared is going to be 2x. And the derivative with respect to x of y squared is going to be 2y, and it leaves that differential dy dx. So at that point, I've taken the derivative, and I want to now solve for dy dx, and that'll give me the derivative of this function, of this relation. I keep saying function. So I'm going to start off, I want to solve for dy dx. I'm going to subtract 2x. That'll cancel there on the left, and also subtract from the right. So that'll give us 2y times dy dx equals negative 2x. And then to solve for dy dx, I'm going to divide by 2y on the left, which will cancel, and by 2y on the right. And that'll give me the derivative dy dx equals negative 2x over 2y. And if I reduce the 2's, negative x over y. So that'll let me find the slope of the tangent line at 1, 2. So I just need to note that 1, 2, the 1 is an x value, the 2 is a y value. And I can substitute that in here for dy dx, negative x over y, to find that slope. So this is going to be negative, my x value is 1, and my y value is 2. And that's what I've got for part A. The slope of the tangent line to the circle, x squared plus y squared equals 5, at 1, 2 is negative half. So once I've got that slope, what I want to do is I want to write the equation of the tangent line. Let me just box this, since that is part A, the slope. So to catch the equation of the tangent line, I'm going to set up the point slope form. So y minus y1 equals m times x minus x1. And recall, with that form, I need to fill in 3 things. I need to fill in x1, y1. So we'll go ahead and do that. That's my point here, 1, 2. So the 1 is an x, the 2 is a y. And then I also need to fill in for the slope, which I just found to be negative 1/2. So that's the line of the tangent line to the circle at 1, 2. I want to convert that so that it's in slope-intercept form. So I'll distribute the negative half, the slope, through the x minus 1 binomial. That'll give me y minus 2 equals negative 1/2 x plus 1/2. And then to get it into the mx plus b slope-intercept form, I'll add 2 And I'm going to call that 4 over 2 so I can combine with that half, and that gives me this equation. Y equals -1/2 x plus 5/2 or 2.5. And that is complete now for part B. So in part A, I took the derivative using implicit differentiation to find the slope of the tangent line. Part B, I've written the equation of the tangent line. And for part C, I want to put the two graphs together. So I want to graph that circle. I also want to graph that tangent line. And it'll be a good way for me to graphically check that that tangent line's a good equation. So remember, for the circle, we graph according to the center and the radius. Our form here, if I just cross-reference with the general form for a circle, x minus a squared plus y minus b squared equals r squared. So remember, my center is given by a comma b. Well, when I look at my equation, there is no a, there is no b, so I'm going to assume that they're both 0. So the center of this circle is right there at the origin. Let's plot that. And then the second thing I need to graph is the radius. So the radius for this circle is going to be given by the square root of whatever numbers there on the right. So my radius equals the square root of 5. Now, the approximate value for square root of 5 is given by 2.236. So I can mark that out, 2.236. That's roughly 2 1/4. So I can mark it there. In fact, what I'll do is I'll mark it on the 4 axes, and I see I've got my scale slightly wrong. So I see that that's going to be 1/4 roughly, 2 1/4 roughly, -2 1/4 there as well. Now there are some points where I know that this circle goes through as well, and it's these points that involve 1s and 2s. So it's 1, 2, and I can see that because that satisfies this equation well. 1 squared plus 2 squared does in fact equal 5. So I've also got that at -1, 2, since the squaring would make that all positive, at -1, -2, and +1, -2. So I can kind of see my circle appearing. Definitely, I've also got it at -2, 1, -2, -1, 2, -1, and 2, +1. So you can kind of create that circle by grabbing points on it according to the radius. So I'm going to sketch that graph. And just keeping in mind, this is our original relation, that circle. So that's a good rough graph. And I want to now check to see if the equation that I created for the tangent line is a fit equation. So it's got the y-intercept of 2.5. It's 5 over 2. So I'm going to graph that there. In fact, let me pick a color that'll pop out. So there's a green. And then the slope is -1 over 2. -1 over 2. And I can reverse that as well. It's up 1, left 2. And that'll give me this equation. So we got to check to see if that's a tangent line. And that rough graph looks excellent because although I am intersecting there on my graph, that's just due to the roughness of the sketch. Well, thank you for joining for this writing of a tangent line to a relation using implicit differentiation. I'll let you write your own tangent lines to your own relations. See you soon.